So we've seen here that if X is doubly ergodic, then X is ME is metrically ergodic. I think Miel will explain this is later. This is not if and only if. Not if and only if. But there is a converse in the fact theorem. Why not? If G act on X is PNP, probability measure preserving. So not just preserving a measure class, but preserving an actual measure and a finite one. Then G act on X squared ergodic if and only if G act on X metrically ergodic. In fact, for PNP action, the following are given. And now I will give just 3 equivalent definitions out of a list that can be made arbitrarily long. In my notes I have 6 equivalent definitions of property, this property, metric ergodicity property in the PNP world that is called weakly mixing. So either of these equivalent definition, and most of the time this one.
Weakly mixing means what exactly?
This. Oh, I'll write it down just okay, I write 1, 2, 3 here, and then I will write the definition. 1. Maybe 1. This is the property that you may think of as stably ergodic. For every other ergodic action, the action on X times Y is ergodic. So this is stably ergodic. 2. Doubly ergodic. These are all property of G acting on X. G acting on X is given, and 1, 2, 3, 1, 2 so far, are properties of the action on X. And 3, G act on X is ME. Any question about this formulation?
Without PNP, how much of this is left?
So we've seen that this implies that actually 1 implies 2 implies 3 is left.
Of course. Yes, that's obvious. And the reverse are false.
And ME implies, 3 implies 1 is what is needed for. So, just a minute.
Is this the same as L2 does not contain finite?
Yes, I said this is the same, if you are familiar with this, as L2x paired to the constant does not contain any finite dimensional subrepresentation. I will not write this one down. G acting on x, assuming PMP is called Wigner mixing. This is just a classical name. And of course there is a stronger notion of mixing, and the stronger notion of mixing is exactly that one that we proved about, the Haumour theorem, vanishing of matrix coefficients. I will not write it down, maybe it will appear in the exercise sheet. Is called weakly mixing if the equivalent property above. Are satisfied. Another remark we have mainly seen. 1 implies 2, I think we all believe that. Implied 3, 2, without assuming. PMP. We'll show for PMP. Same time. Okay, so this is what we do. Any question? So, assume G act on X ME, G act on Y. Ergodic. And I want to show that L infinity x times y is trivial. So take a function here. I want to show that this function is constant. So trick is very easy. Using Fubini, I can think about this function as a map from x to L to y. Right? I mean, for almost every point in x, the function f is defined for almost every point in y. This is Fubini. And I leave it to you to check. The G invariance of the G invariance of the map F is the G invariance of this new map. But this is a metric space. But my ME of X, this is constant. Is a constant in L to Y, and this constant is G fixed. But by ergodicity of Y, these are the constants. So for almost every X, I got the same thing that gives me for almost every Y, same constant. So f is constant. And we get that we get ergodicity. Okay. So metric ergodicity, if you are familiar with, this is helpful to think of as a generalization, a nice generalization of the property known as a weak mixing, which is very important in ergodic theory. Okay. Now, back to SLN. What do we have there? Here. Any questions so far? For SLNR, actually, every ergodic action is automatically metrically ergodic. So, what I just said is completely is bullshit. SL2, SLNR is isometric actions. For example, G acts on G mod K. SL2R acts on the hyperbolic plane with a standard measure and a standard metric. It cannot be metrically ergodic. But what I meant to say is every probability measure preserving action is automatically ME. Every ergodic cell. Okay, so one can deduce this from the fact that actually every action is mixing. This is how move. So you may know this. But let me give an independent proof, or related proof, but very neat in our context. So we need to show and I hope by choice of letters the notation will be clear. For every G map from X to an isometric G action is constant. And in UG. Of course, just by the fact that if X is mapped to the invariant points, the image is constant by ergodicity. If there was no action of X, if there was no action on U, and you try to map X into U, this will be an invariant function into a nice space, and the image must be a point, a delta measure at a point, the image measure. So we might as well assume that, let's remove this subset. Assume now, by contradiction, that there are no fixed points. Either I'm hitting fixed point, or I'm hitting the set of points which are not fixed. Assume by contradiction that I didn't hit that set. X hits the complement. So I'm assuming that U has no fixed points. Or maybe one more word about it. X is ergodic. U has two pieces, the invariant points and the rest. By ergodicity, X will hit one of these. Either it hits the invariant points, and then it must hit one point. And the map from X to U is fixed, is constant. Or X hits the rest. So here I'm considering this case. I'm considering the map from X to the complement of the fixed point. So I might as well assume that there are no fixed point in U. And I should get the contradiction to the existence of such a model. We know now that the action of G on U is proper. Consider the image measure on U. So I think of the image which is pushed to U. And take K in U compact with more than half the memory. Then, what will be the measure of GK? What to be at least? Be at least 1/2 as well, right? And the intersection with K will have some positive measure as well. This is not 0. And this is happening for every G. And this is contradicting properties.
I have a little doubt. You remove the fixed points,
Yes.
and you claim that the rest is proper as well.
No. I removed the fixed point, and then I was assuming that there are no fixed point. So on the rest, G act. G act on this metric space with no fixed point. G is SLM.
Oh, okay.
And this is a theory that we proved yesterday. Every action with no fixed point.
Sure.
And this is a theory that we worked for. It's not a triviality. Okay, so let's gather some corollaries. For example, the action of G on G mod gamma is ergodic. Do you agree with that? You must agree. What about G mod gamma square? Well, it follows from that, right? If it is ergodic, it is metrically ergodic, and if it is metrically ergodic, then the action, because G mod gamma, well, I didn't tell you, but you understand, gamma is lattice in G. For G being SLN R, gamma in G a lattice. So, should be so true. The action of G on G mod gamma square, or actually G mod gamma to the n, I claim, is ergodic. The action of G on G mod gamma square, because it is a lattice, after normalization, this is a PMP action, and because we proved that the action of G on G mod gamma is ME, the action of G on G mod gamma is obviously ergodic, hence by that term it's ME, hence it is doubly ergodic, and the action of G on G mod gamma is ergodic. and stably ergodic, or actually stably ergodic. Now take y to be G mod gamma, and go on, in that. Maybe another, I forgot to do this, it's observation. That I should have done before. G, which is again SLN now, act on X, ergodic, and by the way, metrically ergodic. H in G, non-compact. Then also the action of H on X is ergodic. And actually metrically ergodic. Let me explain this. First of all, why is it metrically ergodic? If I would prove that it is ergodic, metric ergodicity will come easily because just consider the action of G on X squared. It is ergodic as well. And restrict that one to H, it is ergodic by what we are about to prove. And if H acts on X squared ergodically, then it acts metrically ergodic on X by PMP. So I'm forgetting. So why is that? Consider L2XH. Can we have fixed point here? H fixed point. This is a trick that I made before. This is the same. If you have H fixed point, this is the same as a map from G mod H to L2X. Right? I mean, just take the orbit of that H fixed point. Whenever, but okay. Now I just have to say metric ergodicity. And this is the same as, or equivalent to L2X G. This is metric ergodicity of G mod H. Right? I mean, you cannot map G mod H into this metric space unless you hit a G fixed point. And these are the constants. Okay, so this corollary gives me same notation. H acts on G mod gamma to the end is ergodic. With these notation, of course. G is SLN, gamma is lattice, A is non-compact in G. So we get these for free. It's ergodic and metrically ergodic. In particular, H acts on G mod gamma metrically ergodic. And this can be reversed. Third, again, G is SNR, gamma a lattice, H in G non-compact. Then also the gamma action on G mod H is metrically ergodic. actually this guy is followed from a general claim. So G act on G mod H metrically ergodic. So if G act on X metrically ergodic, not necessarily probability measure preserving here. Gamma in G lattice, then also the action of gamma on X is metrically ergodic. Let me give you that one. So, of course, the general claim for X equal G mod H gives that curve. For this general claim, G need not be SLN or anything. So, proof of that. I want to show that this guy is metrically ergodic. So with obvious notation, I want to show that there are no maps from X to U, gamma maps. This is gamma act by isometries here. And this is an actual G space. And I know that G act ME on that one. But unfortunately, there is no G structure here, and this map is only gamma. But if you are familiar with induction in representation theory or its analogs in ergodic theory, this is what I'm supposed to do. This is the obvious things I'm about to apply, and let me do it very explicitly here. So we consider a new map. I will consider a map from G times G mod H to U, just somehow to force some G structural things. So I should take G, comma G prime H to some element. Let me. Yeah, okay. Sorry. In my notes, I was less general. Nothing bad will happen by that. So I need to send Gx to U, and no much I can do. There is no G action on U. I will act before. I will act by G inverse here on X and apply phi. Can you see from that corner? Okay, so this is the new map I'm having, and now, again, if you wish Fubini, I think of G as a measure space. This is a map between two spaces. G is a measure space with the hard measure, X with some measure which is implicit in our discussion, and I have this product space and a map to some nice borrowed space. Again, I can use Fubini and think of this map as a map from X to the space of maps from G to U. And L means space of maps. Actually, I will elaborate on these kind of notations probably tomorrow. Again, on the very definition of the Lebesgue space, etc., which I'm postponing and probably I'm making a mistake here. But so this is the space LGU is a space of all maps defined up to measure 0 from that Lebesgue space G into U. But we have started with an equivalent, gamma equivalent function phi. If we apply gamma to G on the right, or this is like time gamma inverse on the right, this is the right action. It will come as gamma on the left here by inverting G, and phi is equivariant, so it will come here. Right? So what I'm trying to say is this is the space of this is actually the space of gamma variables. Moreover, if I apply G to that X on the left, it is the same as applying G to, I can interchange, since I'm taking G inverse X here, I can apply, I don't know, G prime on the left of that G and on the left of just that X without doing a thing. And what I'm trying to say here is that this is a G map. What I'm getting here. But just to be precise, this is on that space, ignore this gamma here, on the space of maps from G mod U, from G to U, I have two G action, coming from the actions of G on the left and on the right of G. And this map, the maps here that you will get, will be equivariant for the right gamma action, and there will be a left G action, and this map will be invariant, equivariant for that left G action. And I leave it for you to check if this is a formula which basically with my fingers I try to explain, but it is better if you write down if you can see it. Okay, blah, 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 blah. But now, this space, the space of gamma equivariant map from G to U, what I want to claim is as a natural structure of a metric space. Maybe I'll... Assuming now, what I can, that the metric on U is bounded, which as we remarked before, we can assume in the definition of metric modicity, there is a G invariant metric, basically an N1 metric, on the space of gamma equivariant function from G to U. And this is basically integrating the U value over a fundamental domain for gamma. For two guys, alpha and beta functions, maybe I'll write it, elements here, but let me write it explicitly. Functions from G to U, gamma equivariant, I will define the distance, maybe I'll use another method, the distance between alpha and beta to be integral of alpha. Now I'm using the distance in U, alpha x, beta x, dx, and this is integration over G, but on some finite measure subject.
Over G mod gamma.
Over G mod gamma, if you wish. Yes.
But invariant.
Yes, since they are gamma invariant, no, they are not gamma invariant, they are gamma equivariant.
No, but this D of alpha x beta x.
Yes, D of those things is invariant. So just the alpha x will vary if I will. Okay, I will write G mod gamma in there. Alpha x will vary if I apply little gamma to x. Also, beta x will vary. But D of these two things will not, since the maps are gamma equivariant, and the metric D is gamma invariant. So actually, yes, I was about to write that F is a fundamental domain, but this makes sense to write it over G mod gamma. This is well different. I suggested here, and this is bounded by 1, and this is the probability space. So this guy makes sense. So this big D is a G. This is a G metric space. Maybe I should write 1 here to denote that this is big D is the metric campus area. Okay, and since I was mapping X G covariantly into this G metric space, and since X is assumed to be GME, this map here is constant. So it means that this map here does not depend on the X coordinate. Right? This is just same thing. But what is this map? It does not depend on the X coordinate. Well, it means that the map phi was actually constant. ME for G implies that phi is constant. Okay, so what we have done so far. Last lecture we've seen that whenever G, our favorite groups, SLNs, act on metric spaces, well, the action is trivial in the following sense. Either you have fixed points, or the action is proper. In particular, if you consider actions of G on G mod H, coset spaces for H non-compact, you can't have any invariant metrics on these guys. Any G invariant metric on G mod H. We've seen that this implies that you cannot map G mod H into any metric space isometrically. A property that we called metric ergodicity. It is much more powerful property than just ergodicity. For example, and this is what I spent, maybe I was boring you doing, I spent some time doing, this property, metric ergodicity, has better inheritive qualities than ergodicity itself. It passes to subgroups, it behaves nicely with lattices, etc., etc., etc. It goes to power. In the probability measure preserving, it goes to power of the space, this is weakly mixing, etc., etc., etc. So this is really powerful, and the surprise is that it really happens in the nature. It's not something that I just came up with and studied the properties. It's something that happens. And it's something that we will exploit in the future. Okay? So what I want to do now, and probably I will continue next time, this is the end of this chapter, and what I wanted to do is back up to foundation of measure theory and ergodic theory, and to explain the notions I keep using. I didn't want to start with this, like a textbook, start with the preliminaries and boring you too much, but I do want to explain this. So maybe this is not the best time of the day, this is the best time from the logic of the lectures to do it. This one. I will do now. And probably we'll continue tomorrow. And tomorrow is the last day of the week, from lecture's point of view. And next week, I will start with, I will be done with that, and I will start with algebraic group theory at the beginning of the week, and later on, I will use what we will gain from algebraic group theory and from ergodic theory and combine them up, and we will get some results. Okay, so this title now is Foundation of Measure Theory. Maybe it's too bombastic. But so I just want to clarify some notions that we keep using. So start with the notion of a Borel space. whenever I'm using the term Borel space, this is a space with a sigma algebra. A set. Now the space once you put a sigma algebra on it, when G acts on such a thing, Borel actions, it means that the maps are invertible and Borel. So maybe G act on X in that context means, as usual, two things. First, I'm having a map, well, I'm having an action map, G times X to X, which is Borel itself. So here, implicitly, I'm assuming that there is a Borel structure on G. G will be a topological group, probably in this context. Maybe nicer than that, it will be locally compact or locally compact second countable group. And this map will always be assumed to be Borel itself, a nice map in the category, then the product of two Borel spaces is a Borel space. And further, this map should give an action, of course, and it should be an homomorphism into the isometries of X, the isomorphisms of X as a Borel space. Okay, this is just very general nonsense, but
Borel space does not have topology in it.
It does not have topology a priori, but of course, whenever you have a topology, then you have the Borel structure, which is the Borel sigma algebra generated by topological space, by topological sets, by open sets. So, if you had topological space, and if it was, I don't know, a second countable, you had a countable basis of open sets, then the Borel space that you will get will be countably generated. Countably generated means sigma algebra is generated as a sigma algebra by a countable collection. By some countable collection, which I will assume separate ones. Like, it's a metric, not a symmetric, or something like that. Or it's a T0 topological space. Example. Borel sigma algebra, the Borel sigma algebra of a second countable topological space. Another notion, countably separated. A sigma algebra is countably separated. Actually, if it contains a countably generated subalgebra, there exists a countable collection, of course, of measurable sets. Collection that separate points. So again, I said it. A Borel space is countably separated if the sigma algebra contains a countably generated sub-sigma algebra. When I say countably generated, I'm assuming the separation as well. I just don't want my words to be too lengthy. And lastly, very important, a standard Borel space, I'm defining, is a Borel space which is isomorphic as such to the Borel space coming from to a Polish space. And of course, everyone here knows what Polish space is. A separable, completely metrizable topological space. So Polish is an adjective associated with topological spaces, and this means that the topological space is separable, so it has a countable dense subset. And as a topological space, it is homeomorphic to some complete metric space. Example for such, L2 of 0, 1. Another example, 0, 1 itself. Okay? Fact, these two are Borel isomorphic. Fact, all uncountable Polish spaces are, as Borel spaces, isomorphic. Forget topology, eh? Yes? Isomorphic. It's quite surprising if you see it for the first time, but it's not hard to establish. I will not prove this one. I will maybe discuss an analog, a slightly weaker analog of that. But that fact actually gives this power of this nice definition here. Of course, I can discuss the space with 1 point or 2 or countably many, but if you ignore these guys, all spaces you know from geometry and analysis are basically the same. Not all spaces. L infinity of 0, 1 with the non-topology is not. It's not the same, but mostly once they are separable, they are nice enough, they are the same space. Of course, the group actions on that same space could be very different. But as a space, it is all the same space, and this is what we call the standard Borel space, or a standard Borel space. This is an isomorphism class. And of course, so standard implies, I guess by this remark here, finitely generated, which implies finitely separated. Oh, countable. Thanks. Okay, so much about Borel spaces, but I'm not really interested in Borel spaces. Oh, I am, but I'm interested in two kinds of spaces. In Lebesgue space, again, I have two sides in my mind: Lebesgue, Borel. Borel are the targets of arrows, and Lebesgue is the actual spaces I'm living in, and this is a Borel space with some extra structure. So maybe I should start by the following. Do you want to leave now or to spend 5 more minutes?
5 minutes is okay.
5 minutes, okay. Let me not define what the Lebesgue space is, but give you a theorem. Every countable generated Borel space with an atomless measure, or measure class, is Borel of Lebesgue isomorphic. So this Borel isomorphic, but I'm allowing myself to forget a null set. 2, 0, 1, C Lebesgue. Let me sketch this, and this will be the starting point of our discussion tomorrow. So this is some sort of, in a sense, this is a weaker version of that one. But something which is very easy for me to describe. I will do it, I will sketch this. I will take 3 steps. X, my unknown guy, is isomorphic to a Cantor set plus some unknown measure. And let me sketch this, it's very easy. So I'm having X, in it I'm having the collection AN that countably generate my space, and I will define the map from X to 0, 1 to the N by sending X to, well, this is the Cantor set, right? And this should be a sequence. And the sequence is 0 or 1s according to whether I am in AN or not. Chi A N X, this would be my N. And okay, you should check whether this is indeed an isomorphism. So the fact that this is an injection is the separation of points by AN. It is measurable by the fact that the ANs are measurable, etc., etc., etc. In order to invert the map, I have to ignore some null set here, because maybe I'm not on to. So the fact that this is an isomorphism means, for me, this is not Borel isomorphism. This is Lebesgue isomorphism. Okay? I'm only sketching.
But if you ignore this null set, you still have Cantor set, right?
Yes. Correct. Step 2, X is iso to 0, 1 plus some measure. This is also very easy to do because, well, I can just take a standard embedding of the Cantor set into 0, 1, which you show your students by raising points to them. Binary embedding. And step 3, so what do I get? Up to now, my unknown space became a very familiar space, the unit interval with an unknown measure. But now just to standardize the measure on 0, 1 itself is something which is very easy to do. Take a map from 0, 1 to 0, 1, which take the point T to the measure up to T. So it's make everything straight. And here I'm using the fact that there are no atoms, and now you must ignore null set if you want to invert it as well. But
the measure was probability.
also, okay, somehow I didn't define a measure class. In the measure class, when I'm saying a measure class, I'm always assuming it's the class of some sigma finite measure, which can always be assumed to be probability. Actually, I will be, as I was more precise about Borel structure here, this is just a preparation, I will be more precise tomorrow about Lebesgue spaces, and I will be formal in the definition. But this is just a preparation. Okay, so by these 3 steps, once properly proven, which I didn't do, but I I don't care now that much about the proof that's here. This is enough for me. Basically, one sees that as there is a unique Borel space, there is essentially a unique Lebesgue space. And we will discuss this tomorrow again. Okay, I'm done.
So do you claim that there are Borel spaces that do not support measure class?
Of full support?
I'm just trying to understand this theorem. Yeah, of full support.
Let me say there are measures which are not equivalent to any probability measure. Take uncountable set and the counting measure on it. I mean, weird thing may happen. I will touch those things tomorrow, but take L infinity of 0, 1, space of all bounded measurable functions of 0, 1, and observe that this is a C-star algebra. Okay? So it commutative one. So it has a spectrum. So there is some compact topological space, very weird, such that the continuous function on it are in one-to-one correspondence with measurable functions on 0, 1, the interval, up to 9. And there is a canonical measure class on this space. But this is something very weird. Okay, so weird thing may happen if you don't assume some probability or some standardness of things. How much the theory of C-star algebra, so the basics, or anything, von Neumann algebra is known? Yeah?
Not much.
Not much.
That's the measures.
I mean, the theorem by Gelfand that there is a spectrum to a commutative C-star algebra, which is a compact topological space. Is this known? Okay. I will not really use this, but maybe I will remind you.